We'll talk about polyelectrolyte gels, modeling chemo-mechanical interactions.
Okay, thank you very much. So this talk has two pieces. One piece is modeling, and where I am going to really emphasize the mathematical issues in this modeling, or the main, what I think are important mathematical issues. And the second part is how to apply this model, or how I apply this model to a special device, and this will bring us to some questions on dynamical systems that I then would like to follow up somehow. Well, I'll show you how this is. Let's see. Yeah. So the goal of this talk is to explore rigorous mathematical modeling of mechanical flow deformation and electrochemical charged particles, chemical reactions, interactions. So mechanical, electrochemical interaction, how do we set it up rigorously? In the second part of the talk, we will analyze an application to oscillatory hormone drug delivery devices. Okay, so first of all, let me start. So in a way, well, I don't know what motivated what. It's different kinds of motivations. But the device itself is, I find it quite interesting. So I'll talk a little more about it now. So polyelectrolyte gels, we think of them as mixtures of polymer networks and fluid. Okay? The fluid may hold several species of ions, and the network may have electric charge attached. Okay, and then we see several forms of interaction. I will go to this in a little more detail: elastic mixing, polymer, and electrostatic. We see first order volume phase transitions. And then there is a great deal of dynamics, transport and diffusion, with a significant role for the dissipation. And then in the application, so this hormone drug delivery devices, and also I've used this in the modeling of biological gels, in which case the liquid crystal elastomers are coming in, and more recently I am getting into the colloids. Before I go on, let me show you here a picture. So I put this picture ahead of time. Because this would be, I don't know, can you see this? So basically, here you see a domain that is surrounded by this pink interface that sits on a fluid bath. Because, of course, a gel is a material that can take water and can shed water. So it really doesn't quite make sense to look at a gel without really looking at the bath. And this is one of the issues that I found with the existing models that looked at gels and there is no water around. So, and then it's very hard to establish rigorously the concept of permeability or impermeability if you don't really have any water around. So, and this is part of my notation. So omega t, so this is all going to be Eulerian, is the domain occupied by the gel, and that sits in fluid. And the domain of the fluid is R sub t, and the interface between the two, which changes, evolves with time, I call it with gamma. And here n, this case, unfortunately, this is not the nematic director, but is the normal to the surface, to the interface, pointing towards the fluid. So let me, I think, well, let's see, maybe now that we have this light, I could give you another cartoon about how we think about gels. Okay, so you have, if we zoom in into a polymer network, so here we have some polymer chains, right, that somehow are cross-linked, and okay, and so these behave elastically, of course, with some dissipation, and it is a kind of material that for some reasons, one could be electrostatic, is it can take water. So when it takes water, it swells very, very much, and when it sheds the water, then of course it collapses. In a way, in devices, one wants to explore these swelling, collapsing states to really make a gate. So when it dries up, nothing goes through, and when it's swollen, then you can transport things across. Now, one thing that I'll be talking about a lot is, say, suppose that we take one of these elements of the network, right? So then I'm interested in polyelectrolytes, which means that these polymers here, these networks, have maybe some side branches, right? Pretty much like what happens also in liquid crystals. But these branches are usually negatively charged, right? So now all this is sitting in water, right, as in my cartoon there. So, and this water is going to have ions, because whether we are in a biological situation or because we model our material to be this way, so there would be different kinds of ions. There can be different formulas, positive and negative, and then you can see what might happen. And this is really, I think, the basic idea that makes all this work. So suppose that we have a situation where there's a lot of negative ions, right? So then these negative ions are going to call in the positive ions from outside, and they will keep neutralizing, right? So imagine the situation that we have to start with, where, say, very idealized, that everything was negative, that we just had the negative groups. So in this case, these groups repel themselves so much that then the polymer has to stretch, right? So then we pay a lot of elastic energy, because these negative groups have to be really very far from each other. On the other hand, as the positive ions keep coming in and reattaching, so then what happens is that, well, at some point, right, there is not so much repulsion force, so there is no reason for the system to pay so much elastic energy, so it contracts. And as I'll show you in a kind of, we'll talk about this later a little bit more precisely, but so then you can see that there is a state where now this network, these pieces of the network, they are all bundling up on themselves. They kind of remove the water, so when the network contracts, of course the water has to go away, and we have something collapsed. So this is basically, and I think it's the main idea of what goes on in the volume phase transitions that characterize these systems. So a polyelectrolyte shell can actually have phase transitions, volume phase transitions, where there are changes of 500 times the size, the volume. So they are huge. Okay, so in the first part, I'll try to give you some idea, well, at least in the of how am I looking at this. Okay, let's see. Oh no, that's a different issue. So first of all, we will talk about the model for gels, or the model that I proposed, the governing equations. First of all, we are going to look at mechanics. Then we are going to account for the families of ions that are around, including, say, charge groups attached to the network, and then we'll set up an energy law. We're going to look at the hysteresis and volume phase transitions, then how to account for chemical reactions. In other words, that these ions and these groups can react and go into each other or into something else. And let's see, the second part, we will look at this cyclic drug delivery device. And after doing a lot of simplifications into this very general model, we're going to get a system of three-dimensional, three ordinary differential equations. We will look at multiple time scales of the problem, and then this allows us to approximate the three-dimensional system with two-dimensional, with two equations. In other words, there is a manifold where the mechanics, where the not the mechanics, everything, mechanics and chemistry, where the dynamics, I should say, takes place most of the time. Okay, and then we are going to see that this two-dimensional system solutions experience a finite time blow up, and that is really the signature is associated with the phase transition happening. Then we are going to extend the weak solutions, and these weak solutions are the ones that are going to allow account for phase transitions, and show immediately that there are two-dimensional limit cycles, and the limit cycles. Then we're going to take a look at limit cycles in 3 dimensions and see how this fits into the competitive cooperative theory of dynamical systems. Now, why this? Well, this came out of an experiment that we're still working in modeling, an experiment that people, that this group, basically my collaborator and people in the lab took 8 years to set up. And the idea is these people are in pharmaceutics, biomedical engineering, so they try to make devices to deliver drugs, different kinds of drugs. So then the idea is that for treatments that require hormones, it is really as important as the hormone itself, is really matching the frequency of that hormone. So then the goal of this work is to make a delivery device that matches, say, the cycle of a certain hormone, whatever hormone is in the therapy. And so what we have to do is really, out of these kind of systems, to see under what conditions we get some kind of oscillations. So the whole goal of the second part is to see that when I set up a system of this form with certain features, very specific features in a way in terms of chemical reactions, you actually get oscillatory solutions. That's why I have my big motivation into looking at limit cycles and when they happen. Okay, so these are some of the, actually today I'll pass this around. This is a paper that is going to appear in Sayama, should be in the next month or so. And this has most of what I'm going to talk about today, and this is something that we are just finished. And then there is some previous work that appears in one dissertation of my student, another dissertation of student in pharmaceutics. And then we have, this is the robustness of the mechanical problem. And then here is a part for the statics with applications to implantable biomedical devices like bones and stuff like that, pacemakers. And then this is a different kind of twist where the hyperbolic component of the system is important. Okay, so, right, so okay, I'm going to pass this because that in a way I told you through these cartoons, but maybe I just want to call attention to this quantity, phi, and actually you will see phi1. So phi1 is the Pauling fraction of the polymer in this mixed, and let's see, so the swollen collapse are characterized by these changes in volume fraction. So volume fraction, of course, goes from 0 to 1. And okay, here are the equations. So first of all, the hypothesis is that the gel is an incompressible mixture of solid and fluid interacting with its environment. Now, what does it mean incompressibility in this term? Incompressibility means that if you take the fluid by itself and you take the solid, the elastic material by itself, by themselves are incompressible. So now the mixture doesn't change volume locally, we'll see that in a moment, but on the other hand, that does not preclude, say, the elastic material itself to really have very large gradients of deformation. Of course, nobody really forces us to make the assumption of incompressibility. People that apply this method, say, for example, in geology, they cannot make this assumption, but it seems quite reasonable for the kinds of materials I'm looking at. So then we start, there's going to be two indices. I equals 1 always is polymer, I equals 2 is fluid. So here we set up equations, balance laws in site omega t, so it works here too. So inside the gel, and we set up, of course, the also balance of mass and linear momentum in the fluid outside. Okay, so here you can recognize more or less Navier-Stokes equation, since we're going to take this to be Newtonian, right, and incompressible, so that's outside. And inside, so here we have the density. Rho1 is the density of the polymer, Rho2 is the density of the fluid, and now we can write it in this form. Of course, it's the product of volume fraction by the proper density, gamma. So, and of course, since we are making this hypothesis of incompressibility, so these gammas are constant, so the densities by themselves, when they are not in mixture but in pure state, they are constant. And I'm taking them to be 1 for now. And so here we see the balance of linear momentum. And okay, so here we have a pressure, we have the two stress tensors, Cauchy, so this is all meant to be Eulerian. And then here we have some force that I'll specify what it means. Basically, it's going to consist in two pieces. There is going to be a drag force, so basically an action-reaction force between the polymer and the fluid, that of course is opposite and same value, same length. And there is also going to be the part of the Lorentz forces that are going to come because there are ions. And this, we're saying that the mixture is saturated, that there is either fluid or solid, there is nothing else. And in a way, in a mixture, you think of the material occupying both components occupying the same point in space at the same time, but of course they occupy it with different volume fractions. Okay, so, and here we're going to have these velocities, stress tensors, pressures, and volume fractions. And later on we're going to see the ions. Okay, let's see if I could do this well. Yeah, okay, this is just a list of, and I'll try to keep it concentrated here, of the different quantities that we're going to see. So the polymer deformation map. So over there I already wrote the deformed configuration. So omega t as in the picture, the current configuration of the gel, omega would be the reference configuration, gamma t is the interface, gel fluid, F is the gradient of the elastic gradient of deformation, so the gradient of deformation of the polymer. The volume fraction of the polymer is phi1 and the fluid is phi2, 1 minus phi1. And now here I'm putting the free energy density under this umbrella, this capital C. Later on, there is going to be many more things here. There's going to be an electrostatic potential and there's going to be ion concentrations. But for now, the free energy depends on the, of course, on the deformation gradient and also depends on phi. And we'll be more specific in a moment. And the stress tensors that I mentioned. And then immediately we see that as a result of this hypothesis, phi1 plus phi2 equals 1, so the whole mixture is incompressible.
So your solvent and your environmental fluid are different things?
I'm supposing that they are the same. And the reason is that the fluid should be able to come in and out through the surface. So it has to be the same.
So those stress tensors will be the same, or?
Oh, sorry. Well, they are not quite the same. And you'll see in a moment the difference. Because the fluid that is inside the gel is subject to other pressures. Okay, and whereas the fluid outside doesn't have polymer around. But I can make this more specific. This is going to come in a moment. Okay, hold on. This is now this answering your question. So this energy in the case. So far we are in the mechanical case. Still no ions. So we have the elastic store energy function, and this is the mixing energy, which we take to be Florey-Hagens, which gives you the energy of mixing two different components, two different materials. And so this is a term that gives the energy that costs the mixing. This gives, say in this case, polymer-polymer interaction, and this gives a fluid-fluid interaction. And normally these are competing. And these are the volumes occupied by BS by a single molecule of solvent, and this volume occupied by the single molecule of polymer. Normally this ratio is very small, and in many approaches in mixtures you don't see this term. Okay, so if we now do a variation of the energy, as usual, we get the stress tensor. So, and for the elastic material, so we get the elastic part, of course, and then we get the part, so which is a pressure, which is really the stress that comes from the forces that come from the mixing energy. So from the variation just comes this. And this is what in the mixture theory is called the capillary pressure. And then whatever dissipation component we add to the stress tensor, and in here we are going to assume, well, for today it really doesn't matter too much, but yeah, later on, yes, later on matters. We're going to assume that this is Newtonian. And for the fluid, so the fluid you see has only the Newtonian part. Okay, and I guess in this, well, yeah, in this case they would be the same actually, because there are different ways to write this, which at the end of the day are the same, and sometimes we write it so that this part is shared by the two. Okay, now let's see. So now I'm just going to give you a glimpse about the boundary conditions, because there are many approaches where you can see this, but in general we found that the boundary conditions are really very, very, none of the approaches that we looked at has a real careful derivation and treatment of boundary conditions. First of all, this boundary, this interface moves with the polymer. So the polymer network is the one that advances or recedes. So, so this is the velocity of the polymer, that's a normal velocity. Now, when we derive, so to derive boundary conditions, so one could go in two ways, okay? So, for example, there is a set of boundary conditions that Doi has established that basically, so basically what we need in these boundary conditions, one of the things we need, is to say, to be able to establish how permeable is the gel to the fluid. And then in practice, you have gels that are impermeable, meaning that they just don't let in or out water. And in this case, you have maybe a softer elastic material, but that's it. And then there is the other extreme where gel is fully permeable, and basically the water comes in and out completely free. But of course, most of the gels are semi, so are in between. So, and then the way we set up these conditions is to say, okay, first of all, we need to set up a balance of mass of the fluid across the interface. So basically what we're saying is that the fluid that lifts, the amount of fluid that lifts the gel is the same amount of fluid that enters the polymer. And that, of course, gives this boundary condition. So you see, notice that the velocity of the fluid outside, the velocity of the fluid inside the gel, they are all taken relative to the velocity of the polymer. And then here we assume this is some form of non-slip condition, right, where we assume that the tangential components of the velocity, and this is a vector, right, that they are the same, okay? So the tangential component of the fluid outside, immediately outside, and immediately inside is the same. And then, of course, we take a balance of linear momentum across the interface. So, of course, here I'm kind of cheating a little bit because this is not fully balance of linear momentum, because the balance of linear momentum would carry actually a very strange term, a term that is proportional to the square of the velocity. However, if we assume that if we neglect the inertia of the fluid, this is equal to 0. And among other things, we don't know how to take boundary conditions that are quadratic in the velocity. Okay, so, but now, I'm not going to do the count with you, but basically, you see what we have is, say, a type of Navier-Stokes equation, or actually Navier-Stokes outside. And then we have here an equation that is, say, has a Stokes operator for the fluid and has an elastic operator for the solid. So now we have to make the counts and see that all the boundary conditions really are there. And at this point, they are not there yet. We need 2 more, okay? But notice that none of these boundary conditions says anything about the degree of permeability. So now we write here 2 more, right? So this is the normal velocity of the fluid. And this somehow remind me some work that Epifanio had done in this place, where you actually need an intrinsic viscosity at the interface. So here we're looking at this quantity, and this is basically the difference of the forces acting on the fluid. So this is the stress, don't worry about this phi2 here, but this is basically the stress of the fluid, on the fluid inside the gel, and this is the stress outside. And of course this part is also, the pressure is also part of this. And this part is the tangential velocity of the polymer, which just happens to be also the tangential velocity on, let's just look at this way, yeah, and the polymer. So now, what we postulate is that this normal velocity is proportional to the normal component of the velocity, of its normal forces. The balance of normal forces is proportional to the normal velocity, and this tangential force is proportional to the tangential velocity. So it's very simple kind of viscosity law in the interface, and these would be quantities that are characteristic of the interface. So now, if you are in the gel business and now you look at the boundary conditions that Doi had postulated for gel, so in principle you get a little bit worried because they don't look at all like this, and of course you better get some connection with what Doi has got. But then it happens that if we now take the limits, first of all, of this viscosity is going to infinity. So if this viscosity is going to infinity, since these forces are finite, then what we have to get is that the velocities are 0. So in this case, this is the normal velocity of the fluid near the interface. So it means that no fluid is really getting ahead or behind the polymer, so nothing comes in or out. So we have the case of an impermeable gel. On the other hand, and this is the Deutsch condition, and on the other hand, if this velocity, if this viscosity is 10 to 0, then means that the gel is going to be coming in and out at ease, and they actually give the conditions for perfect permeability that Doi postulated. So in a way, you see, if we get this equal to 0, so then it means that the fluid somehow cannot tell whether the fluid near the interface cannot tell whether it is really inside the gel or outside. Okay, so that's one of the, and now here we have immediately an energy law that, okay, so basically the rate of change of the total energy is equal to these dissipation terms, and then we have a term which is, this is the boundary viscosity, and this is the excuse me, that is the dissipation rate function. So this would be the relation, basically. So the boundary contribution and the bulk contribution, so the two Newtonian pieces, and then the dissipation due to the relative velocity of fluid and solid components. Okay, now when we bring in charge. Okay, so in principle we have a family of anions. These are concentration variables, and if you say zk's are the corresponding balances, so this is the total charge of the ions. These ions, of course, can be inside or can be outside. We are going to talk. And then the network has some charge. And here I put this in purpose, although right now I'm not going to do anything with it, but it comes later. So the network has two types of charges. First of all is the charge that came with, with the synthesizing, with synthesis, whatever we did in the manufacturing state. And then here I am considering one of these ions. So, and this is important for the example. So there's one of these ions, and I am going to call it, say, the first ion, C1, that is the one that reacts with the groups in the polymer. So, and then when it's attached, when some of this is attached to polymer, so this contributes to the total charge of the network. And in general, the network charge is negative, so here we take this negative. And this is, I'm thinking that this is the active one, the ion in the fluid that is able to react with the network. And then we have the electrostatic potential, of course, having all this charge, and then we have the dielectric coefficient. Okay, so now here we're enlarging the energy. So remember that this is the energy that we had in the mechanical case. So we have an energy that's inside the gel, and then we have also some energy outside. So inside the gel we have the Coulombic energy. So I am using the vector C to denote the family of all the concentration variables, or here again Pauling fraction. So that's the Coulombic energy. That's the ionic energy. So it's kind of, let's see. So this is the entropy related energy. And same, so the Coulombic energy of the ions in the fluid outside. And let's see, and of course, the entropic contribution of the ions also outside. And these have this form. This we've seen before. Coulombic energies have this form. In general, of course, the dielectric coefficient outside and inside are different. And here we take this. And we don't, well, the reason to take this is the one that gives linear diffusion. Don't have to necessarily take this. And then, of course, this very important is the chemical potential, which is basically a potential energy. So is the same role as the gravitational energy with a change in height, right? So you store energy or you release energy, and in this case, you store energy or release energy with this potential according to this function by changing the number of particles, in this case by changing the concentration. So changes of concentration in a way act as changes of height in the gravitational, say in gravitational physics. Okay, so now here we postulate the Poisson-Nernst-Planck equations. So this is the advection. So here we're saying that the ions are, these ion concentrations move with the fluid, so they advect with velocity v2. Outside, of course, they advect with the velocity of fluid outside, which is bf. And, of course, this is Poisson's equation. What I did here is to write these equations already in dimensionless form because I want to look at a limiting case. So this coefficient here is the Peckland number, which basically gives the ratio between the transport, the velocity, the advection velocity, and say, and the diffusion. And then here we have this quantity R sub d, which has the dimension of a length. So this is the Boltzmann constant, dielectric coefficient. This is the unit charge. Well, this would be the Faraday constant if you want, the Q. And so this is the Debye length. And then we have this coefficient beta, which is the ratio of the Debye length to the typical length, capital L, of the system. So now when, what happens is that Poisson's equation, so if beta is small, in other words, if we have this R sub d very, very small compared to L, so then we could look at the limit beta 0, right? And of course, if we look at the limit beta 0, then what we get is that the sum of the charges locally inside and outside has to be equal to 0. So this is the electroneutral limit. This electroneutral limit is used very much in biology and basically in all applications because usually the type of length scales that one deals with are larger than the typical nanometer, which is the Debye length. So if you have some, some phenomena going on at the nanometer scale, then you have to bring back the full Poisson's equation. And that's why I think this might be important, when we talk about colloids, when we talk about pneumatic colloids. So it is not clear whether, the electroneutral limit is really going to be adequate, especially if the particles, colloidal particles, are big. So, and then in this case, when we go to the electroneutral limit, so we lose Poisson's equation, and then phi, the electrostatic potential, actually plays the role of a Lagrange multiplier that maintains the electroneutrality constraint. Okay, so now, of course, there has been great efforts in studying these equations when are coupled with Navier-Stokes, and this is still a big open problem in terms of analysis, but let's see what we can do here. Now, here I just want to tell, well, a couple of subtleties that this model has, and I'm going to look at, so now since we added the new equations, the Nernst-Planck equations, so we really need to set up boundary conditions. Now, I'm going to look at the boundary conditions in the electroneutral case, because that's the case that is particularly interesting and challenging, I think. So, when we go, okay, so we have the equations that come as natural boundary conditions for the case that Poisson equation is present, okay? And then somehow you can just go through your list and set beta equals 0, right? So, but you cannot always do that. You cannot always do that because beta enters in some places, enters as a single perturbation. So then, to really derive these boundary conditions, one has to do a very careful asymptotic analysis to look at what happens at the limit beta going to 0. So once we did that, then we got 3 conditions here. Of course, we get diffusion equations, so we wouldn't need the third one, right? One is in, but since we have an interface that moves, so basically one of the outcomes is the equation of motion of the interface. So the first thing that we get is the continuity of the chemical potential across the interface. If you have Poisson's equation, you have continuity of the concentrations themselves. Now here the concentrations in general, of course, are going to be discontinuous, and that's why we are alive, because our cell membranes are able to keep up these discontinuities. And then here there is the continuity of the ionic flux. So if we look at here these 2 terms, so this in a way is the flux because of transport, because of advection of ions, and this is the flux because of diffusion. Now, I won't have time to talk about it today, but actually there is a way to reformulate this in the case that the ions are actually big particles. So that would be another case that would be of interest in colloids. And finally, we get the equation of motion of the interface. There is one part, so this is the normal velocity. Actually, I should say, sorry, the velocity of the water, or of the fluid across the interface. So this is the normal velocity. So if you forget about this term, this is what especially biochemists, have been using for, and biologists have been using to study transport of water, say, across membranes. Now, when we do the dynamical coupling, so we inherit this extra force, which is the mechanical force. So, and also our single perturbation analysis, so gives, reproduces the Van Hoff's law, which says that the osmotic pressure, in other words, the pressure that is inside because of the fact that there is these ions, is really the sum of jumps in concentrations. So we're able to rigorously justify, how the mechanical force really contributes to Van Hoff's law. Okay, now finally here for this model, there is the forces, the body forces that I wrote at the beginning. So now there is one type which is friction, which we choose to be proportional to the. It has to be somehow proportional, well, in a vector way, to the difference, to the relative velocity. And then here there is a couple more forces. So first of all, this would be what we would call the Lorentz force, right? So, and then there is another force which is called the Helmholtz force that is not there if the dielectric coefficient is constant. So if the dielectric coefficient depends on the volume fraction, we get the Helmholtz force. It's exactly the same thing for F2. And here just an interesting observation. Probably this is very well known everywhere. But if we had just one component, we would be getting the contribution of these electric forces into the equations would be in the form of a tensor. And that's the Maxwell tensor. However, I have not been able to show that these forces actually come from a tensor. So for what I can say, there is no Maxwell tensor in a mixture. I don't know if that's true or not. Okay, and then finally here we had an energy law, same as before in the mechanical case. So now we have all the full energy with the Coulomb and ionic and the mechanical. And again here we get and again, this would be the rates of dissipation. So these are the mechanical that we saw before. So by the way, these are the viscosities of fluid, polymer, and fluid outside. And that's the viscosity across the contribution to the rate of change of energy at the interface. And the new one is the one that comes from diffusion. Now, let's see. So I'm not going to show you the another part that I do, but a couple of weeks ago when I saw doing his presentation, I realized all of a sudden that this can be done in a different way. Can actually be set up as an Onsager's principle. And when you do Onsager's principle, then you have a much better tool. Because basically now you think, give me a system, right? Maybe very complicated with several length scales. As long as I'm able to set up the relation, at least formally, I can get equations. So, and that's what really works in pneumatic colloids. Okay, so now I'm going to head to the experiment, but here I want to show you, this is an experimental work from somebody at National Institutes of Health. And this is an experiment where there is a phase transition. So this is the volume fraction of the polymer. This is a system that is activated by calcium chloride. And then every one of these points, so this is a static experiment. So, right, so they change the concentration of, in this case, calcium chloride, and let the system stabilize, right, and measure volume fraction of polymer, which, by the way, this is basically the inverse of the deformation gradient, right? So this is one-dimensional. Think about dimensional. So then you see there is one critical ratio where all of a sudden this volume fraction just jumps to much higher value. So this would be a collapse because it's an increase of the polymer. So now this plays a role in the example that I'm going to discuss. And so I'm not going to show you many reactions, but just let me tell you a little bit how this works. So, and then I'll tell you a little bit how we adapt this, our previous setup to model this. Okay, so this is a tabletop experiment for this oscillatory device. So here there is a chamber, and this is the membrane. So this is the membrane that is the gel, and that that can swell or collapse. So then when the membrane is open, the glucose from the body, so the external environment, that would be the body. So glucose is coming in. Now here we have glucose oxidase, which accelerates the reaction. And so then the glucose breaks down into something, into a negative group that I'm not going to worry about it. But here we have hydrogen ions, right? So now, again, when the membrane is open, it's swollen, here there is a drug, so the drug can come out and gets delivered. Now, okay, so but you see when this happens, when it's open, same way that the drug goes out, then also the hydrogen ions go out, right? And now the hydrogen ions don't really quite make it outside because they get trapped at the negative groups in the polymer, right? And so when enough of them have gotten out, then we have the ball in transition and the membrane collapses. Nothing else is coming out. So of course, no drug is coming out and no glucose is coming in. However, these hydrogen ions are not really, not permanent there. I was told that if instead of being, because this is a sodium, well, if instead of, instead of hydrogen ions, say we cut calcium ions with two, of course with two positive charges, so that the result is pretty much permanent. They get attached and that's it. However, this is not permanent, meaning that they start diffusing out. Okay, so they start diffusing. So when enough of them have left, so then again the negative charges that the cartoon I showed you before start becoming active. There is repulsion, right? And membrane swells again. As soon as the membrane swells, then you have again the glucose coming in, and everything starts up. So the goal of this experiment was really to kind of vary the parameters, vary the different kinds of chemical concentrations. Well, I'll tell you what they are. It's fairly simple, the idea. So to kind of tune things to get a certain oscillatory behavior of this membrane, to get a certain period. Okay, so now here, I am not going to talk about the experiment, if I can say a little bit more about before, but here is, this is result of simulations of the equations I'll show you before, but well, this is external pH, so that would be hydrogen concentration outside. And this is some kind of a ratio of one of the ions. And this is another, this is the swelling ratio. So I just want to show that there is hysteresis behavior. However, of course, I haven't shown you hysteresis behavior to what. Okay, let's see. I'm going to skip this. And this is how we write our system. After we kind of pass to a more comfortable notation. So basically phi, again, is the Bolling fraction of the polymer. So, and one thing you see is that we have dropped diffusion. Okay, so this is just what we use. And also we have added the reaction terms that I didn't necessarily have before. Now, if you are interested in seeing how one gets to this, I'll be very happy to explain it later. But this is already the dimensionless form of the system. So phi is the Bolling fraction, which, because of balance of mass, this phi is the inverse of the deformation gradient, which is now just a scalar function because this is one-dimensional. Okay, so you could write here the equation, maybe in terms, if you want, of the thickness of the membrane. That is going to change with time. And these x and z are just two of the concentrations that are in the picture. So x is the concentration of ionized groups, of the groups that have reacted with charges in the network, and z is the pH, the ion concentration, hydrogen ion concentration, inside the chamber. Now, of course, there is other ones, but here we made the assumption that some of the reactions are very fast. So we already consider that when everything starts, they get settled. So, and some of them boil down to just an algebraic equation. And this condition that we see here, where I made some parameters equal to 1 for now. So this basically is comes from the electron neutrality. So now here we have, so in a way this is the stress, the problem, actually the force. And this is the one that comes from mechanics, elasticity plus 4 Huygens. And this is the part that comes from the osmotic pressure. So that is this pressure because of the fact that, of having ions. Now, when I go to our numbers, the typical numbers that the experiments, work with, and by the way, you don't see sodium, you don't see any other ones, because the concentrations are very small. So we have got rid of them. However, it's very important to bring all of them back if you want to write a Lyapunov function, which I did at some point. So then you see here you can immediately see that we have a gap in length scales. In other words, that the mechanics, this is the elasticity equation, of course, dissipative, there is no inertia. So this is a lot faster than the chemical reactions, okay? And so I use this in the analysis. Okay, so now, by the way, so this is basically the stress-strain law, except that it's not in terms of the deformation gradient, but it's inverse. And you can see that we have non-monotonic. What happens is that the device, like all cases that we have non-convex, non-convex forces, non-convex energies, I should say, non-monotonic forces, it's going to happen, all the dynamics is going to happen here and here up to here. So in the decaying branches, which would be in the increasing branches of the stress. Okay, now, sorry, this picture didn't come out very well, didn't have time to make a better one. So think of lambda as a concentration variable. So that gives us, so this is the slow manifold. So in other words, this is what we get. This is an equation. These are the constraints of the problem when we set up, when we get rid of the first equation. So basically, let's see if I can go back one moment. So you see, when I do the right changes of variables, so going to changing time scale, so we end up with a small parameter here, whereas the other ones don't have a small parameter. So then we can say, okay, let's just look at the limit of the small parameter 0. So then we have that in the limit, we have a constraint, that this H is equal to R. And then you see here we have another constraint, which is electroneutrality. So when we plot these constraints, which would be the slow manifold, we rid of the first equation. So it's like the first equation starts acting up, settles down, and then everything else goes. So then what we get is that really the dynamics takes place for this set of variables in the problem. Think of this as x if you want, okay? And of course, here we have the third variable, which is z, which would come perpendicular. So this is the cross-section of a two-dimensional surface where the system lives most of the time. So in a way, it's an inertial manifold. So also what happens is that the system does not visit all the points of this two-dimensional surface, but only visits, again, this part and this part. And I'll tell you why in a moment. Okay, so now, yes?
Sorry, could you remind me what X was?
Okay, X is a concentration. X is the concentration of hydrogen ions in the chamber.
What is Z then?
Z is the concentration of ions here that have been, let's see, it's the concentrations of ions that have been neutralized.
In the gel?
I should say groups, yes. So I have these negative groups sticking out of the network, and then part of them at some time are going to be neutralized by positive charges. So the concentration of those that are neutralized, that's it. So, and then there is a couple of other variables, but they go so fast that we kind of we made the substitution. So then basically here, if we have look at the three-dimensional axis, so we get these surfaces, and the system lives here most of the time. So my goal is to prove that somehow I can get a limit cycle for the dynamics in the right branches of this. Okay, now let's see. Forget about this. I'm not going to talk about what this means today. So now this is x as a function of phi. Again, this is a constraint that is valid on this low manifold. I want to show you this also to indicate that, let's see, that again, the dynamics also happens in here, in these monotonic branches. Now here there is a very interesting thing and puzzled me for a long time, because you see when we go, so this is phi and this is x. So when we go to phi near 0, which means that it's a system that has lots and lots of water, is very swollen. So I was getting this negative concentration. I said, you know, how is this possible? This system, otherwise, you know, for and all the other aspects seems to work. Well, and then I realized that because, you see, this comes from, so we obtained it when we go into the slower time scales. So that we set up when the mechanical equation becomes an algebraic constraint. So what happens is that looking at that very carefully, the scaling breaks down if the system is very swollen. So the scaling is not working here. Okay, so now there is ways to remedy this and what it means. Okay, so now this, I'll show you a couple of theorems. First of all, here, I take A, it's going to be the set of parameters that make sense for the system. And here I take a set of initial data that again is a set of initial data that makes sense. And okay, so here, okay, so capital T, suppose that is the maximum time of existence of classical solutions, in other words, C1 solutions of this ODE. And the null line is this manifold, the slow manifold. So branches of the null line such that H prime is negative, so in other words, the monotonically decreasing branches are globally stable with respect to the three-dimensional dynamic. So it means that solutions to the three-dimensional system are actually very close, so they get very, very close to the solutions of the slow manifold, the two-dimensional manifold. And also, the system has a single unstable equilibrium. Now, also the classical solutions of the three-dimensional system are bounded. So in particular, the volume fraction stays clearly away from 0, which would be extremely swollen state, and 1, which would be an extremely dry state. And the same for all the concentrations, X and Z, satisfy some bounds that depend on the four dimensional parameters of the problem. Now notice that here I get that these basically depend on initial data only, these also depend on initial data, but here I can get bounds that are uniform with respect to, oops, with respect to the dimensionless groups. So that's very, very important in order to get control of the solutions. Now, out of this family, there exists a subset of initial data, so that the classical solutions of this slow system, or the two-dimensional system, blow up in finite time. In other words, they exist only on a finite time, and the derivative of the volume fraction with respect to t goes to infinity as we approach the finite time. And phi itself tends to some particular values, which are basically the extremes of the hysteresis graph, if you want. Okay, so this would be the maximum, correspond to maximum, well, in that non-monotonic graph of the concentrations that correspond to the critical points. Okay, so now if I, so in a way with this two-dimensional system, since solutions don't exist for all time, so we wouldn't really be able to, to do much. In particular, we're not going to be able to get oscillations. So then the first question is, can we actually extend those solutions in a weak sense? Okay, so now we look for weak solutions of the plane system. So what I understand, okay, weak solutions. So first of all, of course, they exist as classical solutions of the three-dimensional system for some maybe finite time, right? Then, so there is time t star, finite time, which will be the capital T of the blow-up result. Actually, that's the blow-up time. So where this phi takes the two critical values, which are going to be the maximum and minimum of phi that the system can achieve. Okay, so now I'm allowing these weak solutions to experience a jump discontinuity. So we are able to extend the solutions by jumping to the other branch, and then we have a discontinuity of phi. So this is basically, well, not basically, it is exactly the volume phase transition, because we just have a jump in volume fraction. Now, the time derivatives of phi, as we approach t star from the left, so go to infinity. So the solutions experience blow up of the first derivative. And the concentrations are continuous at this time. So there's no discontinuity of the concentrations, and this agrees with the phase transition picture that you have a kind of a brusque, very rapid change in volume. However, the concentrations stay continuous. Now here's my theorem that, so if we take now initial data, again in the two-dimensional manifold, then weak solutions of the two-dimensional system exist for all time and have the following properties. Their orbits are bounded. That follows from the previous theorem. The omega limit sets of these orbits do not have any equilibrium point. And of course, this is a consequence of these two, then that there exists stable two-dimensional limit cycle. And there might be more than one, but there is one which has been observed. So we observed those experimentally, and there is more than one which is not the one that we're looking for that also shows up. And so that's what I commented, that the jump discontinuity in the volume fraction corresponds to the phase transition occurring at the critical pH. And but now, if you now look at the system from the three-dimensional point of view, these solutions are not discontinuous anymore. In fact, this gap in the volume fraction, this jump in phi, is not such a jump when you look at the problem as a solution of the three-dimensional problem. And in fact, what happens is that the first equation, the equation that we kind of got rid of, so it's the one that makes the connection between the phis in the phase transition. In other words, if you look at the phase transition from the point of view of the whole system, it is a very fast, very sharp transition, but it's not a discontinuity. So what happens is that the fast time scale shows up only in the phase transitions. And it shows up also if you go to a very, very swollen regime, which we don't in this case. Okay, so then pretty much here the conclusion is that solutions of the three-dimensional system remain in the two-dimensional manifold for almost all time. They reach the third dimension to realize the phase transition. And so Claudia, when I was talking to her the other day, says, you have a canard. Okay, so it's basically a three-dimensional limit cycle that relaxes to a two-dimensional one. But of course, I was not happy here because I've got limit cycles of the two-dimensional system, but I have not got limit cycles of the three-dimensional system. So very, very quickly, I'll tell you then what comes next. Okay, now I wrote these. Okay, so basically, this system also fits into the theory of competitive cooperative systems. And I got this idea when I read the paper by Hal Smith and the co-authors on the dynamics of the HIV virus. So it's actually very, very close to some regime, to the persistent regime of the HIV, where people kept getting a little better, but then the virus comes back, and it's not, they don't go to the full healthy equilibrium state, or they don't go to the full, virus invasion overtaking the organism, but you get that it balances, it comes back and forth. So people get better, then get infected again, get better. So that's the kind of dynamics of this membrane. Okay, so here I'll skip this. So basically here I just wrote the definition of what we understand. This is a theory for three-dimensional systems. I suppose it can get extended. There are some extensions for this, but a lot of the work is explicitly done for 3D. And So, and then we have this kind of relation. This is inequalities among the components of these vectors. Then we have the concept of p-convexity, which is basically a convexity condition when the two vectors are ordered. And then we say the system is cooperative if all the off-diagonal entries in the Jacobian matrix are positive, and competitive if they are negative. Now, this work showed that this is really implies or is equivalent in some sense to some kind of monotonicity property on the vector field of the equation. Now, the good property about these systems is that have three-dimensional limit cycles. Okay, and this is Kirch's theorem. So a compact limit set of a competitive or cooperative system in R3 that contains no equilibrium points is a periodic orbit. So in a way, this is, in spirit, pretty much the Poincaré-Bendixson theorem in 2 dimensions, but for 3-dimensional systems. Now, of course, do these properties are these properties satisfied in our case? So when we look at our Jacobian, right? So what we basically have to look at is the sign of the diagonal terms. So they are all positive, and there is one negative. So, but however, if the negative is symmetric with 0, then the results still go through. So we have a cooperative system. What is really interesting in our system is to show that this is negative, and we can do this because of the estimates that we get on the solutions, right? So I told you at some point that this is an estimate that we can do independent of the non-dimensional groups, and then also because of the fact that the branch, the manifold, the slow manifold of the 2-dimensional system is stable, and actually is very strongly stable, in other words, globally stable. So then what happens if you start with your initial data, say away from that manifold, so then very, very quickly approaches the manifold, and when you are very close to the manifold, then this condition is satisfied. So then in a way, okay, so then it holds in the neighborhood of the null line, but it's not a local result in a way, because we know that the solutions are going to end up there anyway. So, and then once they end up there, so at that point, we have this condition. So now we can say that the system has, the 3-dimensional system has a limit cycle. Okay, I think I'm going over time. So sorry, I rushed through. Oh, and this is, of course, the punchline. So this is that we did, well, there's simulations with MATLAB for the 3-dimensional system. So these are oscillations on the volume fraction. These times are dimensional times. And these are oscillations in 2 of the chemical concentrations. So, and in fact, these numbers really match very well, the experiment by the group of Ron Siegel, and even, even the times when you change some of the parameters. So basically, the parameters that we can control is the salt concentration and the glucose concentration, and of course the cross-sectional area of the membrane. That's very important. Its width. That's very important, how it is in the reference configuration. And then some features of these ionic groups, some features of the side groups. So, and also we can control, how many, what is the concentration of these side groups when the polymer is manufactured in a way. So, and there is quite a good range of glucose. It's just, so the parameters are very sturdy. It's not that we just pick up some values. It's really a very, very good range. Like, for example, for glucose, we have an order of magnitude of 100. One of it is maybe a little unrealistic. Now, okay, so then, as a conclusion, I'll say that this as a tabletop experiment worked very well. But we have really not much hope that this can actually be one day implanted and, and used for hormone delivery. And the reason is that, you see, this works very well from the point of view that it works at a pH of 7 outside. So we can make it even almost 7.4. But now, you see, in the body, we have bicarbonates. We have all these bicarbonate groups. What the bicarbonates do is they go around the body and make sure that the pH is kind of stays the same, right? So they keep the pH stable. So then keeping the pH stable here means that they kind of suppress completely the mechanism for oscillation, because in some gels you have oscillations, you have phase transitions, say with temperature, but here is a phase transition which is triggered by gradients of pH. So, and then if the body regulates the pH so that doesn't like jumps, so it's killing this. So if we put bicarbonates, you can see these oscillations fizzling very quickly. So I don't know if the chemistry, they tell me is relatively simple. I don't know if they can find, it would have to be a completely different kind of chemistry that we don't have any idea. Okay, so sorry for the overtime, and I'll be happy to talk to you more about the different aspects of this if you're interested.
So the questions?
Yes.
Is it clear that the system in the experiment is at the same point in this cycle all the way along the membrane? Or is there some sort of
Yes.
out of phase?
Yeah.
behavior?
It is, yeah. So in this experiment, well, to start with, we got rid of space dependence, but in reality, this transition happens just very, very near the surface. So, and it is actually not necessary that the whole membrane collapses, through, but as long as it collapses, as soon as it closes down in the layer, and that's what they see. But now, of course, there is another inconvenience, is that you saw that all these energies are non-convex. So that means that when you have a non-convex energy, things like to develop domains. So then one of the problems is that this interface starts undulating. So, and after a while, it just doesn't quite, everything goes a little bit strange.
But interesting.
Yeah, it's a very nice problem, and it's a problem I use it, to start learning about some of these things. Instead, you see general theories, but when you apply them to this, it's for specific problems like this with a nice experimental background, it's kind of satisfying. Now, of course, what I'm working on the PD system, and here I would really like if I can have some advice from the dynamical systems community. So basically, to keep we have also oscillations if we keep diffusion. So the simulations also suggest that this is happening, but the analysis goes in a very different direction. But I think it's doable because the reduction to 2 dimensions is still true. So there's a number of things that one can do.
You made a comment about the Maxwell stress and mixtures, and I didn't catch it. What was that again?
Okay, let's see. So when you account for, okay, so we go back here, right? So here we have all these. Well, in the energy, we have, of course, Coulombic. You have the ionic energies and so on. So in special, look at the Coulombic part. Then let's see. I think it's this. So then you get the contribution, of course, of these of the Coulombic energies in terms of conservative terms, right? And of course, that's what they are. That's very well known. And, however, if you had a single component system, the way we see this contribution appearing is in terms of maximum stress. Another thing, well, what it really means is that this force is not the divergence of anything. It was just a curiosity. I don't know if it's because I spent some time trying to see if I could find a Maxwell stress for mixtures, and just couldn't come up with it. So maybe it's well known that it happens or it doesn't happen, but.
Any other questions or comments?
So did you say that this 3D Poincare-Bendixson result did actually apply?
Yes.
Or okay.
Yes. Yeah. That's the theorem. But somehow I
well.
like the 2D approach also, so I didn't want to get rid of the 2D approach.
If there are no other comments, we'll have a chance to talk with Carme privately as well. So let's thank her again.